Okay, so welcome everyone. I hope you do see the slides for my talk. Good morning.
Yes. We see the slides?
Yes, we do.
Okay, good morning. First of all, I would very much like to thank the organizers for inviting me to speak. It's not easy to organize a conference over the internet. It's not easy to organize a conference in So I'll be talking on the main topic of this morning's session, the algebraic constructions of cages. So I will try to explain what I'm talking about, and I'll tell you about some of the results that we have obtained with my colleagues. I would like to contradict the introduction in the sense that if somebody wants to ask something, please do ask right away. Even though the rule is you're supposed to raise your hand, I don't mind when people ask me. It makes me feel that people are listening. So if somebody just turns on the mic and asks a question, that is fine with me. Well, unless too many people do that at the same time. Okay, so let me start with the presentation. I'll be talking about graphs. The word cage maybe did not reveal the fact, but I'll be talking about graphs. And I'll be talking about I will be talking about the graphs where I know the length of the smallest cycle. So I'll be talking about kg graphs. So those are graphs where each vertex is of degree k and the smallest cycle is of length g. So it does have cycles and the shortest cycle is of length g. So these are, of course, special graphs in a sense, but there's plenty of these graphs. What I'll be interested in is the sort of most efficient graphs with these parameters. And in this talk, most efficient means the least number of vertices. So I will be talking about graphs with prescribed degree at each vertex and prescribed girth, and which have among all the graphs with these properties, the smallest order, the smallest number of vertices. And this order will be denoted by nkg. A smallest kg graph. Finally, we're getting to the main term from the title of my talk. So one of these smallest graphs among all the kg graphs that has the smallest order is called a kg cage. I should just warn right away, there could be a unique one or they could be several graphs of the same order. So that's why I say a kg cage. So that's the introduction. This is going to be my topic. I will be looking for cages. And so I will be looking for graphs optimal within a specified class and optimum with respect to the order. Okay, so this is, of course, a well-known problem. You can find it in the literature under the name the cage problem. And the cage problem stated with what I already used is if somebody gives you a pair of parameters, k and g, then you're looking for the order of the smallest graph in which every vertex is of degree k and the girth is g. And you are supposed to find this order, and you are also supposed to find at least one graph of this order. Okay. This just tell you which part of graph theory this is usually considered part problems where you have a specified class of graphs and you're looking for one with some extremal property. It's also a optimization problem if you want to think about it this way, because you have a class of graphs and you're looking for the one with the smallest number of vertices. And it's a two parameter because we are looking for answers for all possible pairs, k and g. I should say something that, of course, people who are working in this area already know, and that is if you just grab a pair of numbers k and g, it's not even immediately obvious that there exists at least one graph like that. with every vertex of degree k and girth g. But I will address that right away. That's a classical result. That the answer is yes. There's always plenty of graphs, and actually the set of graphs with these parameters. We're searching a set that is defined. It's well understood, but we don't know how to construct all the graphs. So it's not like we can take one by one and keep going toward the smallest. Okay. And the other thing that is important in this area, that these are large problems. The classes of graphs are infinite, and the smallest graph may be rather large. As k and g grow, so does the nkg. Okay, so it's a problem where we know what we're looking for, we know what the class is, but we don't have an efficient way to construct all the graphs in the class, and we don't have an efficient way to keep going from larger to smaller. And the other thing I want to say is people often solve problems of this type by taking a KG graph and making it smaller, but this is very hard in this area. There are some properties to make it smaller and still keep the properties. Okay, so it's a computationally demanding problem. It is usually solved with lots of computer power, and it requires the search of an infinite set that cannot be efficiently constructed. I'm trying to stress that this indeed is a very hard problem. Okay? And then you could probably ask, if it's a hard problem, why do you want to know the answers? There are many reasons for that. Of course, I, as a mathematician, I just do want to know the answer. But there are many applications of cages, and let me just list a few reasons. First of all, many of the network designs rely on a regular graph, which means all the vertices are of the same degree. And as I understand this, that makes the production of such things easier. You can mass produce those knots with the same number of outgoing wires or something. And the other question, why do we choose a small graph? I think that's fairly obvious. If you're going to make something, it's better when it has fewer parts than lots of parts because it's cheaper to produce. The other class of applications is an application in coding theory. Small graphs of large girths are often used in constructions of the so-called low-density parity check codes, which are linear codes, error-correcting codes, and the fact that the girth is large speeds up the decoding. So this has applications in coding theory as well. But I should say these are two chosen selected applications. There are more applications of cages as well. So I'd say it's an interesting mathematical problem. It's hard to solve, and it has many applications. So that makes it interesting to me, and I hope to most of you as well. Now I'm going to really start thinking about the problem. So remember, we have the given k and g, and we're looking for the smallest graph with those parameters. And I'm listing three easy examples to just give you an idea what these graphs look like. For instance, when k is 2 means each vertex is of degree 2, and the girth should be n, so the shortest cycle should be of length n. Then obviously this is it. This is the graph. It has a cycle of length n, and each vertex is of degree 2. And if it's going to have a cycle of length n, it cannot have fewer vertices than n vertices. So this really is the smallest graph in which each vertex is of degree 2 and the shortest cycle is of length n. And you immediately recognize why the answers will have to grow, because with the growth of the girth, you will have to be seeing larger graphs. Here's another extreme sort of case. This is a graph where each vertex is of degree n-1, and the girth is 3. And the smallest graph with these properties is obviously if each vertex is of degree n-1 and it has at least one vertex, so it has at least n vertices. This graph has n vertices, and each vertex is of degree n-1, and I have tried the graph where the girth is 4, because we all know that a bipartite graph cannot have an odd girth, cannot contain odd cycles in general. Okay, so here are 3 easy examples. I'm not after these. This is just to give you an idea what some of these graphs look like. I'll be after beautiful examples. And I will list some. There are many beautiful examples of cages, but here are some that I will try to sort of start off from. There's the Peterson graph, where each vertex is of degree 3 and this length of the shortest cycle is 5. For instance, the outside cycle is 5. Of course, you should verify there is no shortest cycle, but trust me, there is not. The next example is the smallest graph in which each vertex is of degree 3. That's easy to check. And the girth is 6. You will find a 6th cycle very easily, and you will not find a shortest cycle. And the last example is the so-called graph, which is each vertex. These are all cubic graphs. Each vertex is of degree 3, and the shortest cycle is of length 8, and no shorter cycles than 8. So I will say these are beautiful examples. I will explain this more precisely, but even just by looking at it, you can hopefully agree that they are nice. Very quickly, some history of the problem. Officially, people think of the problem starting in 1947 with a paper of Tat on a family of cubic graphs. So that Tat graph appeared in that paper. Then so that was in 1947. After that, there was not much activity on the problem. Then in the 1960s, Hoffman and Singleton came up with an idea they learned from their colleague Moore, and they spoke about the Moore graphs, and that is the official start of looking for the best possible graphs. And then there is but it was a very important result in the area. I promised to at least mention that if somebody gives you the parameters K and G, I claim that there are always infinitely many graphs with these parameters. This result goes back to Erdős and Sachs, and I think that's a good reason to mention this result. Erdős also had his hands in this problem, and they proved with Sachs that there are infinitely many graphs with these parameters for any K and G. So the question is meaningful. It makes sense to look for the smallest one. It's fairly obvious that there will be a smallest one because there's a finite number of vertices. Okay, so here's Paul Erdős. And to give you an idea about the sizes of things or orders of the graphs, here's a classical result by Sauer from 1967, who has proven that G is odd, and when G is even, it's multiplied by 4. Okay, so the important thing is these bounds tell you that we're talking large graphs. When K and G, especially when G is large, this is a large exponent, and we're talking about large graphs, which makes the problem hard in terms of searching. Okay, and so I will just list this. Any construction gives you an upper bound, so you know that the order of the smallest graph is obviously less than or equal to the order of any existing graph with these parameters. So any construction gives you an upper bound. In terms of lower bounds, there is the classical result of Moore. As I said, if I read things correctly, this was a professor who didn't want to publish, so his 2 colleagues published his result. Of course, they also added their own results. Most of you probably have seen it. Those graphs that have the order that matches this Moore bound are called Moore graphs. But we will not spend a lot of time with these because these are very special graphs. Okay, so just to clarify again, so we have a lower bound on the order that is universal. If you get K and G, your graph cannot be smaller than the number that you can calculate from the Moore bound. And if you hit this Moore bound, if you can have a graph with that exactly that number of vertices, obviously it's the smallest one because no other graph smaller exists. But it only happens very rarely that your life is this easy, that you can construct a graph. And it's not that we are not smart enough. These graphs generally do not exist. They only exist when you have the complete graphs. You already saw those two examples. Of course, those are the smallest graphs. I already argued that, the complete graphs and complete bipartite. Girth 5 and the degrees 2, 3, 7, and 57. There could be the first three parameters, the Pentagon, Peterson, and Hoffman Singleton are known. This 57 is a big open question that has not been solved for a very, very long time. So just in case you want to leave this lecture with an open problem, which if you solved it, you would become famous. The question is, if there is a graph of degree 57, each vertex of degree 57, the girth is 5, and the number of vertices is the number given by the Moore bound for the numbers 5 and 57 and 5. Nobody knows whether the graph exists, but if it does exist, it will be somewhat of a surprise because it must have very different properties from the other examples. The rest of the Moore graphs are special graphs that come as incidence graphs of generalized polygons. That's a very famous part of finite geometry. And again, there aren't that many of them, and all of them are even girth. So what this list means is from now on, we have no idea what is the order, what is the NKG for given K and G. We only know a lower bound, and we know that for most pairs, we cannot reach that lower bound. So for most pairs K and G, all you know is that your graph has to have more vertices than is the Moore bound, okay? And so finding cages, once again, this is a real problem. We have a class of graphs, and we're looking for one that has the least number of vertices. So how do you solve such a problem? I already stated it's impossible to construct all these graphs and then go one by one and look for the smallest one. We don't even know a way to do this, that you go from a larger to a smaller in some kind of a systematic way. So usually you solve this problem in 2 steps. First, you need to have a very good construction of a KG graph. Usually you have a general construction. You don't have a single one construction, but you have a general construction for different pairs of K and G. What I mean by good, it produces a graph that is not very, very far from the Moore bound, but even that is vague. But if you have such a construction, and you start believing that there is no smaller graph than the graph that you can construct, then you should also prove that there is no smaller graph, okay? So this is really not easy. You need to have a construction, and then if you can't get any better than that, and you start suspecting that that's the best possible, then you have to prove that it is the best possible. And in fact, in some way, the second part is even much harder because we don't have very good tools to prove that there is, well, the problem also is that our good constructions are still very far from the lower bound. So there is a big gap and we don't know much. So for that reason, people settle for the first step, and that is they look for good constructions, okay? That is the game I like to play as well. So we're looking for good constructions. Given K and G, I want some universal constructions that produce a KG graph that is relatively small in some sense. And of course, these are hard numbers. We can compare these numbers. So if you have several people trying to construct a smallest KG graph for a specified pair K and G, then they can compare the orders of the graphs they obtain, and the smallest of them is called a record graph. Yeah. So this is a part of mathematics where you can have a world record. Once again, and what that means is you can construct for a given specific pair K and G a graph that is smaller than any graph that anybody else can construct for this specified pair. Of course, this needs to be somehow tabulated and followed. So for that reason, there exists a dynamic survey paper where if you find a graph that's smaller than the graph listed in the dynamic survey paper, you notify the authors of the survey and they will check whether your graph really is a better graph than the previous one, and then you get into the table with your name in it as well. So it's really, if somebody wants to do mathematics because he or she is competitive, this is it. You can see what other people have achieved and you can try to beat them at their game. Okay, so here's an example of a table for the cubic graph. So that's graphs where each vertex is of degree 3. So this is how the tables look like. I'm sort of showing it to you to inspire you what the game is played like. So for instance, 13 is the first order, girth 13, I'm sorry. So we're talking cubic graphs, girth 13. So the pair is 3, 13, degree 3, girth 13. The best graph that is known at this point has 272 vertices. Nobody can prove that it's the best possible, but the lower bound that comes from the Moore bound is 202. So this is what I mean. Your graph that, well, not your, this graph goes back to Mackay and Myhrvold and Hoare. This graph is the best that anybody has constructed, but it's very far from the lower bound, and we don't know whether it's possible to find a smaller. So for the time being, these people are listed here as the authors, and the order is listed here. So if you ever run in your career into a graph where each vertex is of degree 3 and the girth is 13, count the number of vertices. If your graph will have fewer vertices than 272, then you will replace Mackay, Myhrvold, and Hoare in this table, and the order of your graph will be here and your name will be here. And that's basically how all the lines appear for the graph. For instance, for girth 20, the smallest graph that anybody has found is due to Jeff Exo, my colleague from Indiana State. And his graph is more than twice larger than the lower bound from. So it's very far from the hypothetical lower bound. And as you move further through the table, for instance, here, the lower bound, so the smallest graph that may theoretically exist of girth 25 and degree 3 has could have 12,000 vertices. The best graph that anybody knows is, again, due to Jeff Exo, has 108,000. So you can see that we're roughly 8-9 times larger than what theoretically, hypothetically we could be finding. Okay, and the table keeps going. This is the real end of the table. Beyond the girth 32, we don't record anymore because the graphs become too big. And you can see that the lower bound is 131,000, while the real construction has 3,600,000 vertices. So the difference is quite big. Okay, this is due to Bray, Parker, and Rowley. Okay, so this is how you compare your results with the already known results. You go to the table, and if your graph is smaller, that's a reason to celebrate because your name will be listed in the table fairly soon. If your graph is larger, you're too late. Yeah, unless your construction has some inner beauty that will make it worthwhile and people will like it. In terms of having a record, you're too late with your graph. Okay, so that's sort of the competitive side of this area. It's not surprising since we're optimizing and we don't know how to optimize to the limit. we record the best we can do, and then we compare our results within the research community. Okay? And so if somebody asks how to become a world record holder, I do have to say that should not be your goal from the very beginning, because it's very hard to get into the tables. They don't change very often. And so it's a lot of hard work. Okay. So, but it's not impossible. And the way to do this is one possible approach, and that's the one I'm going to promote in my talk, is to sort of look at the examples, the known best graphs, and try to guess what are the properties that make the graphs so successful. And then stop searching through the whole entire class of graphs and just search through the graphs that look promising. Okay, so again, this is a meta principle, but it's a good one. So we have a very hard problem and a very large class of graphs, and we have some examples of successful graphs. So we look at the examples and try to learn which properties make them successful, and then we search for the best graphs within this more limited class of I did it on purpose. If you look at the beautiful examples, they are really, really very special. And you will notice that all of them are so-called highly symmetric graphs. So they have lots of symmetries. And I will try to convince you that that's not sort of a just something that happens. There is a good reason why highly symmetric graphs are good candidates for optimal KG graphs. So looking by the examples suggests to me that we should be looking within the class of highly symmetric graphs. And here is a little bit more of a justification. So we don't just observe this. The fact is that highly symmetric graphs look all the same at each vertex. I will be a little more specific about this, but it really means that if you sit in any vertex of the graph and look around fairly far, it looks the same from each of the vertices. Yeah, the local structure of the graph is the same. And so if for highly symmetric graphs, if your local structure does not contain short cycles, then the entire graph does not contain short cycles. And this is really important news. So once again, if I'm looking for a graph that doesn't contain short cycles, one way to do this is make it locally not contain short cycles and carry this information all over the graph, and then if no vertex is close to a short cycle, then the entire graph, if it's highly symmetric, contains no short cycles. So this is really one of the important reasons why highly symmetric graphs perform so well in this area, because you sort of have to take care of the local situation, the local picture, and then thanks to the high symmetricity, this property gets carried over to every other vertex, so there are no short cycles. Okay. The other reason why it's good to look at highly symmetric graphs, and this is a practical reason, very practical reason, is symmetric graphs have usually compact descriptions. What I mean by that, we're talking about looking for graphs of very, very large order. They are even hard to store in the computer. They are hard to search for properties and so on. So it's good when you have a much shorter description of the graph. And that doesn't usually happen if you do calculations. Of course, most graphs don't really have a short description, but highly symmetric graphs usually do have a compact description based on some group theory or algebra. And that is an advantage, because then you sort of search through the compact descriptions, which are shorter, and then you have a better chance of finding something. So these are the two intrinsic reasons why looking into highly symmetric graphs is a good idea. So, okay, to be more precise what it means, highly symmetric, I will just remind you of what is a graph automorphism, because a symmetry of a graph usually is also called a graph automorphism. So it's a bijection on the set of the vertices that maps edges to edges. So if U and V are adjacent, so is the image of U and the image of V under this bijection, and vice versa. So it's if and only if, really informally. A graph automorphism is a mapping of the vertices that preserves the structure of the graph, the structure being which pairs are adjacent, which are not. And the more automorphisms the graph has, the more symmetric it appears, because this really means that if you have a vertex V, and whatever it looks around the vertex V, the same it will look around the vertex phi of V, because the automorphism carries over all the local information. So if you have lots of automorphisms, lots of vertices look the same, and you're getting what I was promising, that if you have many automorphisms, then you only need to check the neighborhood of one vertex, and wherever the image is of this vertex, you don't have to check that, because that's guaranteed by the property that it's a graph automorphism. Okay, so highly symmetric, I'll be more precise. I'll be talking mostly about vertex transitive. Again, most of you have heard the term, but it's simply a graph where you have a graph automorphism that maps any vertex U to any vertex V. That's exactly what we are after. There are no exceptional vertices. All the neighborhoods of all the vertices look exactly alike, because between any two vertices there exists a graph automorphism. That means a bijection that takes the neighbors of the U to the neighbors of the V, the cycles around U to the cycles around the V. So all we have to do for vertex transitive graphs is much simpler than the general graphs. We look into the neighborhood of one vertex. If that neighborhood contains no short cycles, we're set. We know there are no short cycles in the graph because all the other neighborhoods look the same. So knowing beforehand that the graph that we're dealing with is vertex transitive dramatically cuts down on the time needed to verify the girth of the graph. The other comment is all the known Moore graphs are vertex transitive. So this is sort of a support of my claim that this must be an interesting property. I will even do a little more. I will go through these are not anymore Moore graph. Well, Peterson is Moore, but even if you go away from the Moore graphs, the record holders are also highly symmetric. The ones that are in red, in fact, are vertex transitive, but so that I don't lie, a cubic graph of girth 7 is not. The smallest cubic graph of girth 7 is not vertex transitive, but it still has a large number of symmetries. The next one is the TUT graph, which is highly symmetric vertex transitive, and the next one on 12 vertices comes from an n-gon. It's again highly symmetric. So yes, I admit not every known record holder is vertex transitive, but they show up quite often. And even the ones which are not vertex transitive have a considerable number of records for an infinite set of parameters when you have some kind of a special construction. So one example like that is the sextet graphs or the Lubotsky-Phillips-Sarnak constructions. Both of them are highly algebraic. The topic of my talk is using algebra in this area. The sextet graphs are based on finite fields. The Lubotsky-Phillips-Sarnak graphs are Cayley graphs, and this is the one class that I will define in this talk. Okay, so the majority of the best constructions take advantage of symmetry, and I already argued this. Yes, let's look for symmetric graphs for given degree and girth. Okay, for girth 6, I'm still sort of arguing for my main reason for this. For instance, Lars, Miller, Chiageva, Shiran, and Tomanova proved that all of the smallest known vertex transitive graphs of a given degree are even Cayley graphs. Cayley graphs constitute a subclass of the vertex transitive graphs, but a very important subclass, and I will be focusing on these for a while now. Okay, so what is a Cayley graph? So once again, I'm not cheating you. I'm still talking about vertex transitive graphs. all the Cayley graphs are vertex transitive, but it's a subclass that is even better understood, and it's often believed to constitute the majority of all vertex transitive graphs. So here comes the algebra. A Cayley graph starts from a finite group, gamma. It has from a generating set of this group that we will close under inverses, meaning we throw in the inverses for each element, but we don't want the identity in the set. And then the Cayley graph is constructed from the group by having the set of vertices identical to the elements of the group. And two vertices are joined if you can get from one to the other by multiplying by one of these generators. So the vertex G, whatever G is connected to the vertex gx1, gx2, all the way to gxk. Since the xi's are different, these are different elements, and each vertex of a Cayley graph is of degree k, where k is the cardinality of the generated set. Here's a quick example. I will go very quickly. This is an easy group, Zm cross Zn. Here's a generating set, 1, 0, 0, 1. Of course, you can get every pair from these. These are their inverses, and this is what it looks locally around the vertex 0. Neighbors of 0, 0 are the vertices that you get by adding the generators to 0, 0. Easy to check that this is a degree 4. And if you do it for all the vertices, you end up with this nice rectangular grid. You should realize that this and this is identified, and this is identified. So it makes for a very, very nice and very, very symmetric graph. And that's my example of a Cayley graph. Of course, most examples are much more complicated. This is an easy group and an easy generating set. Of course, the next question, if you're gonna limit yourself to considering only Cayley graphs, you should have a guarantee that they even exist for every K and G, because I already said, yes, Erdős and Sachs proved the existence of a graph for any given degree and girth, but their graphs are far from being Cayley, far from being vertex transitive. They're huge, 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 and not very symmetric. So the question is now, if I'm going to restrict myself to studying Cayley graphs, do I have a guarantee that even in this class, I have infinitely many examples? And the answer is yes, but it had to be proven. The first result along these lines goes back to Norman Biggs, which is 1980s. Some of you may know the Algebraic Graph Theory book by Norman Biggs, so that's the same Biggs, who proved that for any specified K, that you will have infinitely many graphs of degree K and large girths. There is no limit on the girth, but this doesn't prove there is a graph for every K and G. It just says that for every K and G, there is a graph of this degree and girth at least G, but it could be much bigger. I will skip the proof, although I want to advertise the proof. It's a beautiful example of a very, very, very clever construction. And it just hits you in the, when you read it, oh, this is beautiful. Okay, so this goes back to Biggs, and the graph is K-regular because it's Cayley, and the proof that the girth is at least G is really cute. Okay, in terms of vertex transitive graphs, let me remind you that that's a larger class. So it was first proven by Neděla and Škověra in 2001 as a byproduct of some other nice theory they developed, that you do have a KG graph for a vertex transitive KG graph for every degree K and every girth G. So this answered the question for vertex transitive, still didn't answer the question for Cayley, but we finally managed with Josef Sheeran to prove in 2009 that for every pair KG, there exists a Cayley graph of degree K and girth G. In fact, infinitely many. So it does make sense to look for the small Cayley graph with the parameters, with the idea that the smallest Cayley graph with these given parameters has a good chance of being at least a record holder. Okay. Once you start looking into Cayley graphs, then you have to try to understand the structure of those graphs. And the important thing with respect to the cage problem is how you determine the degree and how you determine the girth. The degree is obvious for a Cayley graph. It's the number of elements in the generating set. I already argued that. So how about a cycle? And it turns out, and I will sort of go quickly through this. It turns out that the shortest cycle in a Cayley graph, the length of the short cycle is the length of the shortest word in the generators that's equal to 1. The non-trivial means not 1, and reduced means I don't do x inverse because those cancel. I cancel all the obvious products, that element followed by its inverse. But I look, so this becomes a group theory question. I have a presentation for the group, a generating set, I have the group, and the question is, what's the length of the shortest word in the generators that's equal to 1? Okay, so a word is a sequence of generators, shortest sequence of generators that's equal to 1, non-trivial, reduced. So it becomes completely group theoretical question. Okay, so when you look again at the example I started with, I will not have to work hard to convince you. You take then xi xj times the inverse times the inverse. This is reduced because I don't have an element immediately followed by its inverse. But since this group is commutative, I can move this around, and this word is equal to 1. And so the girth of this is at most 4. And in fact, it's not shorter. So it's exactly 4. As you could see in the structure, the graph consisted of 4 cycles. Okay, so abelian groups are bad for constructing large girth graphs. Okay, so what I'm going to really go quickly over is the idea that you want to determine which groups are good for constructing graphs of large girths. Okay, because if you want to use Cayley graph construction, you need to determine which groups are good for large girth, and it's not the abelian group. Okay, we already argued that, I quickly argued that in an abelian group, you can always find a 4th cycle. Okay, so if you want to construct large girth graphs and you want to do the Cayley construction, you have to reach for groups that are far away from abelian. This is not exactly what I'm doing on this slide. I'm considering the so-called nilpotent groups, and those are not all that far away from the abelian. In fact, they are considered often the closest groups to the abelian groups. The shortest lower central series for nilpotent groups is actually the abelian groups. And so this is, in a way, a generalization of the abelian groups. I apologize for not guiding you through the definition, but the point is, if you want to do group theory, use it. If you know that abelian's bad, try to determine what is also bad, or what are the limits of related classes. And nilpotent groups are related to abelian groups. And we were able to prove that if you have a finite nilpotent group, the nilpotency is the length of the series, and it's generated by a set of size at least 3, then the girth of any Cayley graph, this is important, this is a general result, the girth of any Cayley graph that uses a finite nilpotent group of nilpotency nu is limited by a square of this nu. So that means that if you want to construct large graphs with large girth, you need to keep increasing the nilpotency of the groups you are considering, which means you're increasing the complexity of the groups you are considering. So yes, I do advertise for this approach. It's a nice approach. It does produce very, very, very nice graphs. It starts from groups, but if you want to keep competing with others, you have to keep considering more and more complicated groups, which in some way is fantastic from the point of view of a mathematician. It means that I will have to get my hands dirtier and dirtier as the problems get larger and larger. Okay, here's one other class of results, and that is if you want to move even further away from the abelian groups, the other class that is well known are the so-called solvable groups. Okay, so that's another class of groups. In general, solvable groups are further away from abelian than nilpotent. Nilpotent groups and abelian groups are solvable, but solvable groups contain other classes of groups which are not nilpotent, and they have a still better chance to succeed in constructions. And so I will just say another class of groups that goes further away from the abelian groups, which are hopeless, are the solvable groups. You can find the definitions for solvable groups. They are in my slides too. But the point is, if you have a solvable group with a derived series of length n, then this length. So in comparison with the previous result, if the nilpotency was nu, then the girth was bounded by a square of nu. Here, if the solvable group has derived series of length n, the n goes into the exponent. So that means that these solvable groups, which are not nilpotent, have a much better chance of producing graphs of very large girths. And I'm listing all these results to give you a taste of what it means to be using groups in this setting. The point is, you need to learn which groups are good and which are bad for the constructions, and then you try to reach for the ones that you still can handle, but they are promising. Because of course we could do a lot of work with very, very, very complicated groups, but then we would have to understand the structure of these very, very complicated. So you always try to find a sweet spot where you still stand a chance of constructing something new and interesting based on groups that you still can handle and understand. Okay, I will of course skip the proof. Here are more precise numbers which are based on constructions. So again, there are for some parameters and girth, we have better information, but that was the the exponent, the length of the derived series in the exponent. Okay. Okay, I had prepared some further examples. This would be a nice example, sort of just to support what I'm talking about. I already mentioned girth 14 construction by Hoare. It's a Cayley graph. So again, when you just try to learn from previous examples, yes, Hoare used Cayley graphs. And for girth 14, he has a record holder. And it was then improved by something called a voltage graph construction, which is a generalization of Cayley graphs. And since I cannot talk about all of our results, I would like to leave you with an idea what this is all about. The idea is to construct cages. Yes. We construct record graphs from groups, and we construct record graphs by learning enough about what makes a group suitable for a record, and then using the right group, and with the use of computers, making it still accessible. With the use of computers, we try to look for records. So there are further examples of this approach. There is the approach of Lubotsky, Phillips, and Sarnak, who in fact used non-solvable groups for their constructions, because that moves you even further from the abelian groups. And you do, in this area, you want to move as far away from the abelian groups as possible. All of the examples are not solvable that are really, really nice. I will not get into this topic, unfortunately, but there is something called a voltage graph construction, which is a combination of group theory and so-called derived graphs, which are graphs that are constructed from smaller graphs by using the group theory. The voltage graph constructions proved to be even more successful than Cayley graphs. So eventually we went through this, but it is a generalization. A Cayley graph is sort of a voltage graph from one vertex graph based on a one vertex graph. So voltage graphs in general can start from more vertices and then you don't get Cayley graphs, but we can manage and control the girth of the resulting graph based on the girth of the bottom graph. And so we got a lot of results along these lines, which often beat the Cayley graphs because we have even more possibilities. Again, the advantage is we have a small graph, but by blowing up things, we get a very, very, very large graph where we still have control over the very, very large graph. So that's, again, one of the ideas used in these areas. So I will skip the voltage graph construction. I apologize. I hope my slides will be posted somewhere. And if somebody wants to my slides, of course, I'm willing to share them. Here are two examples of how you construct, for instance, the Peterson graph from the dumbbell graph by assigning elements from Z5 and so on. So those, again, are arguments for saying, look at the known examples. So Peterson is a known cage. Hewood graph is a known cage. Try to figure out how those are constructed, what makes them special, and then try to repeat this for other sets of parameters. So Peterson and he would suggest to use the lift, the voltage graph lifts, and yes, it does deliver. Lots of the record holders are actually constructed using the voltage graph construction. And I listed for you some of the basic results that predict how the voltage graphs will perform. And I will really go quickly over this. Certain games are played differently, but in a similar way. You again are asking what's the shortest cycle. And I apologize for going quickly through this, but I do want to show you this theorem. If you remember solvable groups Cayley graphs, the girth was limited by 4 to the n. If you go into the voltage graphs and solvable groups, the girth is limited by 6 to the nth. So that's one of the reasons why you can beat Cayley graphs with voltage graphs, because things change slightly. And even though someone might say that 6 is not much more than 4, which it is not, but in terms of finding a better graph, you of course reach for the one that delivers better results. Yeah. So I will finish with some few comments, and that is what are the limits of these things? Well, the one good thing is the current record holders are usually constructed with voltages. One way to do this is to use non-solvable groups, but things get much harder when you try to use non-solvable groups. Just determining the girth, the shortest girth is hard. So that's that much. And the last comment is, in fact, something I will leave you with two results of mine and my former student Slobodan, who will also be talking. And that is sort of counter to what I've been talking about. And that is, if you want to stick to vertex transitive graphs, then you positively know that you will be moving away from the Moore bound. Yeah, we don't know in general. Maybe that's necessary for all the cages, that the bigger the parameters, the further the order of the cage must be from the Moore bound. But we don't have that result. We do have the result that if you stick to vertex transitive graphs, so the class I keep advertising in this talk, if you stick to this class, you will pay the price of eventually moving away from the Moore bound. And in fact, our result says that the absolute majority of the graphs, KG graphs that are vertex transitive, will be far, far away from the Moore bound. And we were very glad to obtain these results with Slobodan, because this gives you a very deep insight in what are the real limitations of the approach. I would like to thank you all for listening, and I hope Peter will allow me to answer some few questions, but if not, I will slides to those interested and so on. Thank you.
Thank you very much, Robo, for this very nice talk. It was a pleasure to listen to, and I believe we have some time for questions. So if anybody wants to ask a question, now is the time. So it might be a good idea to unmute the microphone if you are asking some questions. I see some unmuted microphones. Okay, I have a question, Robo, if I may.
Yes, of course. You're the boss.
Not really, but I will come to that shortly. You mentioned in the first part of your talk that the constructions, they are very far away from the moor bound, and the larger the girth is, the larger the gap is. Then you find the smallest example that has these properties. And also at the same time, you said that you want to sometimes disprove there is no cage with these specific parameters. How far can you go, or how large is the gap that you can cover with these proofs? Is it also growing, or is it constantly distant away from the moor bound?
This is a question that I only have to answer with a little bit of embarrassment, but no, it's not. Now, the results for non-existence are very, very close to the moor bound. We are proud of results where we can show that there are no graphs of order moor bound +4. Yeah, that's already being able to show that there is no KG graph of order moor bound +4 for specified KNG. That's already hard. And the known constructions huge, and we're not making much progress with the proofs of non-existence. Yes, we are moving. The original results were moor bound +1, moor bound +2. Now we're much better. We can do moor bound +4, but it's just a constant, and the known constructions are multiples. So the answer to your question is we're not even getting proofs yet that would be a proof that would show that there is no graph twice the size of the moor bound for an infinite class of parameters. That would be something fantastic. I have not seen that, and I don't even know where I would start with that.
Okay, thank you. Yes. Any further question? Is there any further question, please? It doesn't seem this case. So before we move on to the next talk, I have a favor to ask, Robert. By mistake, the technicians that are running the workshop, they gave you the host, not the co-host. So you said you are the boss. No, technically that's not true. You are the boss now. And I ask you, please, could you give the host rights to